Okay, it's good to see you back in this course, ABE161. Today, this will be our last topic for the reinforced concrete structures topic, and also it's going to be the last topic that's going to be included in our midterm exam. All right, let's get started. Isolated footings. So we already discussed the beams and then columns and slabs, and now we'll be discussing in details the reinforced concrete footings. So recall that footings are structural members. They are actually the ones carrying the, if you could say it this way, they're the ones that carries the entire load of this of the structures. So, for example, we have let's say floors. Okay, so we have floors here, and then let's say we have roofing in this upper portion. Okay, so basically the entire loads of the roof, they are transferred. Let's say the roofing sheets, they are transferred to the trusses, and oh, and of course that's including the purlins and everything. Okay, so live load, dead load, and then once they're transferred into trusses, then the truss will transfer the the loads to the attaching member. So in this case, the truss is attached to a column, but there are also cases wherein if you, I mean, you can design also a truss that's being supported by beams. So in this case, then the beam will transfer the loads to the columns, and then the columns will transfer to the footings, and then the footings, they are designed in such a way that they'll be able to provide a proper support for the structure. And in this portion for the floor, let's say the floor loadings. So the floors, the slabs, they're transmitting the forces, the loads to the underlying beams, then the beams to the girders, and then the girders to the columns, and then columns to the footings, then the footings to the underlying soil. Okay, so meaning that since footings are they have a they're actually, I mean, it's common that they have a wider area simply because that the soil has lesser strength, or let's say capacity, as compared to the steel materials or concrete materials. So in that way, by spreading the area, by spreading the forces, so in that way, it'll be able to, I mean, the soil will be able to support the loads. Also, another function of the footing is to prevent the settlements. So it has to be designed in such a way that there will be less settlements and, let's say, slidings or overturnings. Now let's move on to the types of footings. There are actually many types of footings, and we can only discuss a few here. This one is, it's a footing that's supporting a wall. Okay, so if that's the case, then this footing is termed as a wall footing. If a footing is supporting a single column, then the term is isolated footing. And if a footing is supporting multiple columns, that's going to be a combined footing. And the last one here that we'll discuss is termed as the pile caps. Okay, so let's discuss the difference between this. There's still other types, but we'll just discuss these four types here. The first one is a wall footing. So basically, it's just supporting a wall. So wall in itself, it has also um, weights, or let's say dead loads. So it has to be provided as well with a wider area at the bottom. For isolated footings, this area can be, or let's say this geometry can be a square or a rectangular cross section. And when you say isolated footing, then it means that it's just supporting only one column. So this one isolated footing, it can be loaded in a concentric manner. So meaning that the column loads is along the centroidal axis. It is also possible to have a um, this footing wherein you have this configuration. So instead of being at the center or at the centroid, then it is actually offset, or let's say eccentric. Now this will be common for, let's say, for for footings along the property lines. So meaning that you cannot extend anymore. So meaning that you have to design the footings in this manner. The next one is combined footings. So combined footings, basically they're just like isolated footings, except that when you when you try to, let's say, provide a footing, then there's going to be an overlapping distance here. So instead of having, um, I mean, instead of having two separate isolated footings, then you just have to design it in a combined configurations. For this one, for pile caps, these are common for s- soil conditions wherein the hard layer um, is far from the natural grade line. So instead of supporting the structures in terms of bearing pressures or bearing capacity, it can support the structure by frictional forces along these piles. All right. So now, this topic actually will be only focusing on isolated footings, and more specifically, we'll only discuss in details the square footings. All right. Now let's discuss the loads on footings and the soil bearing pressure. As I've said earlier, that the loads from the columns, it can be concentric, or it can also be eccentric. And if the loadings is concentric, then the simplified um, pressure distribution would be a uniform one. But if it's going to be eccentric, then you're gonna have a varying pressure distribution from the soil. However, in reality, different types of soils. I mean, since we have different types of soils, like for example, we have a clay soil, sandy soil, and even the combinations of the main types, the pressure distribution is actually not uniform. For example, we have, let's say, sand. So if the soil is a sand, then the pressure distribution would be something like this. And if the soil type is a clay or any type of cohesive soils, then the pressure distribution would be something like this. So you see that the pressure distribution is not actually uniform. But in analysis, what we do is we just simplify it into a uniform distribution. Okay, so since I brought this up, these different types of soil, then it must be understood that different types of soils will have different types of bearing capacities. Now, um, where do we obtain these values of the bearing capacity of different types of soils? So first one, it can be obtained using the principles of soil mechanics through the service of a geotechnical engineer. Okay, so meaning that you're going to have a soil test, and the soil test will generate a report or will provide an information regarding the bearing capacity and probably other details of the soil. Now, in the absence of this geotechnical report or soil test, then there's also data provided in the NSCP and in I think in National Building Code, where it specifies the different types of soils and then what's the allowable or permissible um, bearing capacities or pressures at a given minimum depth. So it's also included in our lecture handouts, and we'll just discuss probably some few here. So for example, in NSCP, now it says that for, let's say, for well-graded sand, the allowable foundation pressure is 75 kPa. And there's also other details where you can find that. In the National Building Code, what's good is that it has also provided the minimum depth of footing below the adjacent virgin ground. For example, this is the footing, and this is the grade line. Okay, so let's say it's a compact coarse sand. The allowable pressure is 75 kPa at a minimum depth. So what's the minimum depth? And it specifies 0.6. Okay, and there's also an adjustment or some kind of factor wherein you can increase this value if you have an increasing depth beyond this minimum depth of footing. Now let's go on to the derivations and code provisions. Now the first general requirement for the design is that um, the proper design of footings requires that the load capacity of the soil is not exceeded. Okay, and then number two, the excessive settlements and rotations, they must be avoided. And then the third one, adequate safety against sliding or overturning. Okay, so that's the basic idea for the design of footings. Now, for the minimum requirements of foundations, the NSCP also outlines the, let's say, the minimum thickness. For example, this is our footing, and this will be our, let's say, our elevation view. Now, the thickness of footing will be this one. Okay, and then the depth of footing and this one is the thickness of footing, or sometimes in the calculation we call that as the height of footing or height of concrete. Okay, so this is the depth of footing, or depth of footing. Okay, so it's from the natural grade lines. And then what else? We have this footing width. And now to solve for the area must be solved using the unfactored loads divided by the effective soil pressure. Okay, so meaning that if this is our footing, then we'll have a soil pressure distribution here, and that's gonna be our Q effective. And of course, since this is a column, then we have dead load and also live load. So if the equation requires us to have an unfactored loads, then meaning that we can write it this way: D plus L divided by the effective soil pressure. Now, how do we determine this effective soil pressure? The equation is simply the Q allowable. This Q allowable is taken from the tables or the geotechnical report minus the summation of this or let's just write it this way. So the unit weight of concrete times the height of concrete plus the unit weight of soil times the height of soil. Okay, so if we draw it here, it's like this is our let's say this is our allowable soil pressure from the table. And we have a weight distribution from this concrete. Okay, so let's just draw it here. Okay, so this is the, let's say, P sub C, meaning pressure from the concrete, which is just equal to the unit weight of concrete times the height of concrete. And what's the height of concrete? It's just this one. And since we have also, let's say this is our grade line or our natural grade lines, then of course you'll notice that there's also loadings from the soils above the footings. Okay, so meaning this soil above the footing, it also induces pressures. Okay, so let's say this is the distribution. So P sub S is equal to the unit weight of soil. So by the way, the unit weights of soil and concrete, they can be obtained from data times the height of the soil above the footing. Okay, so if this is H sub C, then this one would be H sub S. Okay, so now how do we determine the effective depth of footing or the thickness of footing, this H sub C? Now you notice that we also have shear capacity of concrete, so the depth of footings, they're actually determined based on the shears. Now for the shear in footings, we have two types of shears. So one is called a one-way shear and the other is called two-way shear. So it's different from the one-way slab or two-way slab. This one, when I say one-way, another term for that is called as wide beam shear, and this one is referred to as punching shear. The difference between the two is can be illustrated this way. Now recall that we have loadings from the columns and we also have pressure distribution at the bottom. Okay, so when you say one-way shear, it's actually shearing off this portion of the let's say the footing width. Okay, so at some distance right here, so that would be the critical section. Now it's also the same if you take a look at this side or the other sides. Now for square, then that one side is already enough. Okay, so since we're just dealing with the square columns, then we can just look at it in this one perspective or one side. Now it's just like saying that it's actually breaking off at this section, at this critical section, and this critical section is at a distance d. And recall that d is the effective depth from the top face to the to the to the reinforcing steel, except that in here there's no reinforcement yet. We're just actually establishing the minimum depth that we should have in order to be able to carry the loads. So that's gonna be our basis later on for the design of the reinforcements for flexure. Now, for now, let's just focus on the shear forces in footings. So this is the one-way shear. Now another one is the punching shear or the two-way shear. It's actually something like, because you have loads here and you have also loadings at the bottom, then it is possible that the footing will fail in a manner that that the column actually punches, or it separates, it breaks at this critical section. Okay, so it is actually probably going downwards, and then this one is going upwards. So this will be our critical section, and we will discuss this in detail in a while. Now, for now, this distance from the face of the column will be d over 2, and that will be also true for on this side. That's going to be d all over 2. So we're actually going to get two values of the distance d. So what would be the d if this will be the condition, if it's in two-way shear? Then what will be the value of d if it's in one-way shear? And later on, once we get this value of d, then we can actually use that to solve for the flexural reinforcements. Now, if you take a look at the details of this one-way shear, this is our pictorial view of the footing. And we have this distance, the column width, we designate that as letter C. And the distance from this face to the critical plane is the distance D. And this beam width is, we designate that as P, and the other dimension of the footing is, we designate that as L. Now, if you take a look at the plan view, it's like this. So this is our column, this is our center lines, and this is our column width. And you'll see here that the critical section is actually at a distance d. Okay, so meaning that's going to be the something like a failure point on the footings. Now, in order to solve for the minimum depth, then we have to analyze the shear capacity of concrete, and then also we have to equate that to our shear loadings. So again, we will be computing for the load sides and then the resistance side. Now this will be, the shaded area will be our tributary area. Okay, so if we take the distance here, since this is C, this is D, and if you do the math, you'll get this this relationship here, or let's say the distance. So it's L over 2 minus half of the column width minus D. Now for one-way shear, our shear capacity of concrete is given by this equation. Theta times, actually this is not theta, this is phi. The reduction factor is 0.17 lambda times square root of fc prime times b times d. Okay, so this one is the beam width, and this is the depth. This one is the typical compressive strength of concrete. In let's say megapascals. This one, the depth should be in, let's say, millimeters, and then this one, it should be in millimeters. And this lambda is the concrete modification factor. And we just take that as lambda is equal to 1 for normal weight concrete. Okay, so unless otherwise specified, then we'll just use this lambda is equal to 1. Now, I guess I'm running out of time, and we'll continue this discussion in the next video.